Scientists have probably figured out why bowhead whales can live for 200 years and not get cancer despite being so massive, which is quite unexpected and called Peto's paradox, the observation that larger animals don't actually have higher cancer rates as we would expect, since cancer is just a random process, and if with more cells and a longer life, you'd expect to get more cancer. But this is not at all what we see. Cancer mortality rates actually don't correlate that well with body mass. They actually tend to go down as animals get larger. But why is that? For a long time, the answer to this paradox has thought to be the fact that they have more tumor suppressor genes. For example, right above my head, it says that elephants have 20 copies of the p53 tumor suppressor gene, while we only have one. And that gene is mutated in most human cancers, so it stands to reason, they can just tank more mutations because they have more copies that need to be mutated. However, that's not what they found in bowhead whales. They only have one copy of the p53 gene, and they actually require fewer mutations after that gene is mutated. Instead, bowhead whales prevent cancer by being much better at repairing their double-stranded DNA breaks, which is a big reason that cells become cancerous. They have 100 times the amount of a specific protein called CIRBP, cold-induced RNA binding protein, and that helps shore up double-stranded DNA breaks and ensure that the homologous repair mechanism that looks at the homologous chromosome and says like, oh, okay, this is what we're missing, let's like split that in here and repair it. That repair process is much more efficient and causes fewer mutations in the bowhead whales than it does in humans. And when they expressed that same protein at higher amounts in fruit flies and blasted the fruit flies with radiation to cause their DNA to break, the fruit flies that had more of this protein lived twice as long as those that didn't, showing that the protein is transferable and it really is repairing the double-stranded DNA breaks. Okay, so it's great that evolution's found a way to spare larger, longer-lived animals from high rates of cancer, but why hasn't it done that for smaller animals? Thanks to a new paper, we actually have a pretty good answer to that, and it's fascinating. Follow along if you want to know.